Hello, welcome to this video about optimization. So basically what we mean with optimization when we're programming is that we are maximizing or minimizing some function. And we're not doing it in the normal economic way of taking the derivative and putting it to zero. We're sort of letting the computer help us solve our problem and finding a numerical solution. There are a bunch of different ways to do this, so I'll go through them, showing you an example with just normal agent utility maximizing, and then I'll talk about how you would find indifference curves, which sort of also relates to optimization, but is instead of sort of maximizing, minimizing, it's root finding basically, and then I'll show you a bit advanced how to put this into a Python class and how that would look when you're solving a module. And putting it into class sort of, I think we discussed this, it's sort of a nicer way to solve models, and you can have your functions and everything collected at one place. Yeah, this is obviously useful. Most economic models contain optimizing agents solving a constrained optimization problem. So yeah, I'll also show you that. So just not just optimizing something, but optimizing something under constraints. I'll show you sort of how to do this yourself, and I'll also show you how to use a SkyPy package for scientific Python, which sort of does it a lot better than we can do it. So in practice, you'll typically use this, but it's nice to know a bit about how it works, and sometimes it's also relevant to do it yourself in certain situations. There's a link to the documentation for SkyPy. It's actually relatively nice. I'll show you later, but it's sort of, don't be afraid to look at the documentation for SkyPy once you're getting a hang of it. So the first easy way to do it is to just loop through possible solutions and pick the maximum value that you find. So the example we have here is sort of, as I told you, a utility maximization agent. So his value function is the maximum of the utility function under the constraint that his expenditure has to be lower than his income, that the prices and his income are above zero, and that he cannot consume negative values of a good. And we'll work in practice with the case of the utility function being just a Cobb-Douglas utility function. And then the idea with looping is just to sort of create a grid of x's that are possible solutions. So you can consume zero, you can consume some of your income, or you can consume all your income on one good, and the same with good 2. And then because we're sort of just looping through spending nothing on good 1 or all your income on good 1, and also gridding with spending nothing on good 2 and all your income on good 2, but it's sort of obvious that this situation where you're spending both all your income on good 1 and all your income on good 2, then you're spending twice your income. So we still have to keep the condition here of expenditure being lower than income. And we create grids to do this. And sort of as a new thing, we'll be using a Python file which has stored all the function which does most of the things that we're going to do today, which means you must import it. So when you import custom modules, you'll typically start out with these lines inside of the notebook. They're sort of IPython magic lines. And what they does basically is that when you make changes to your own Py file and the functions inside that, then when you run them inside the notebook, then you don't have to reload everything to see your changes. If you didn't understand that, then just keep this in always when you're working with custom notebooks or custom modules. and pi files. Okay, so we run this. And then I can sort of, I'll open this pi file. So I can just press it and open it. Another way to do it is to use F12. Then VS Code will sort of guide you to the source. So if I don't just press F12, I sort of mark the pi file I'm working with and then press F12. The source also works when you want to find the source code for different functions. Another nice thing in VS Code is that you can sort of have both notebooks and your pi files open. So this is our pi file where we can write sort of raw Python code, which can then be called from the notebook. The reason this is really nice for workflow, because you can sort of have a lot of lines of code, which sort of maybe can be a bit daunting, and then you can have your notebook, which is really nice and concise, and sort of show what you have done. You can talk, you can write a little more with text, and you can make it sort of pretty, and you can have sort of the brute code in another file, where sort of everything is stored. It looks less nice, but it's more structured than the code blocks. So we import this, and inside your pi file, then all the modules that you use inside that pi file, you also have to import at the start of the file. It doesn't have to be at the start, but it's always nice to sort of define what you're using. And it's also like the scope of the pi file is local. So that's why you have to import these, but sort of everything you define in the notebook doesn't automatically come into the pi file. It's more the other way around, that when we're importing this pi file, then everything that's inside of here comes into the notebook. So we just import all the functions from this pi file. We do that by saying from gridsolve import star, which is basically all. We could also like just write the names of the functions that we import. So we can write import ufunc, and then you get ufunc out. And then we can write comma find best choice, and then we get the find best choice function out. But it's sort of easier. It's a little less transparent, but it's easier to just use the star. And then we inside the notebook we also want some packages, mainly for plotting, because we want to plot the solutions that we find, and here just define the u function locally in the notebook. Don't know why that disappeared. Okay. Yes. So now because we have imported this function from gridsolve, then we can just basically run the function and get a solution out. Of course, if you only look at the notebook, then you just okay, I've imported this find best choice function, and then it prints out a solution. We can see that the solution is close to correct. It's numerical and a bit imprecise, but sort of we have an alpha of 0.25%, and you're using 25% of your income on good one. So that makes sense. But we have to go into the pi file and see what's actually happening. So what we're doing is this thing we talked about of just looping through possible solutions. So you create a tuple of like a grid, and then we create empty values of x1 and x2 inside this grid, and empty values of utility. And then we say, okay, our best guess is nothing. You spend nothing on good 1 and nothing on good 2. You keep all your income, and what's the utility from that? And that will be 0 and not good, basically. But that's our initial guess, and we just need any initial guess, and then you sort of find the correct answer later. So we loop through how many grid points we want for the rows for this, like different types of x1s, and how many different types of x2 we want, and then we fill out the x1s. So here we're doing chained assignment, so we're both filling out the numpy array with our x1 values, which we were storing up here, and we're also sort of locally inside the loop creating a variable called x1, which is just easier to use later, so we don't have to carry around this sort of huge expression. Yeah, and the way we created sort of this, when I goes from 0 to n1 minus 1, then this will sort of start by being 0% of your income is spent on P1, and then it will sort of like this move up and up and up until you're spending 100% of your income as you iterate and I becomes larger. Yeah, and then we need some conditions to be met. So first we're checking, okay, is our total expenditure lower or equal to our income? If yes, then we can just put in the utility as the utility function. If not, then we're sort of in a place where, okay, this can happen in reality. So we just input that, okay, you're actually spending 0. And then we know it will not be the best guess, because that we have sort of already guessed that. And then we check whether or not this new utility we have found is better than our best one so far. And if it is, then we store it as our new best one. So x1 best and x2 best are sort of the x1s and x2s. You can also just write x1 here, sort of the same. And then our new u best is the utility for these new x1s and x2s. And maybe we'll print the solution. So that's after the loop. You run through the whole loop and find the best solution in this grid of possible solutions. And then there's sort of a keyword argument for printing, which is the default is true. And then the print function is just a function which is prints what x1, what x2, what is utility, how much of the income is spent, and how large a share of the income is spent on good one. So it's sort of a very simple function, just sort of prints out information. And we'll also return a tuple with all these values. So x1 best, x2 best, so the solution and its utility of the solution. And then sort of these grids of values of all the possible solutions. So that's what's actually happening when we run this one line of code. So this is sort of where it sort of gets a bit nice, that you can have this all the ugly code inside a Py file, and then in the notebook you can sort of say, okay, I've made a function that finds best choice this way, and you sort of have to write a bit down how you do it still, but you can hide some of the ugly code. Now we want to plot the solution, so we just unpack this. So when you run this, then Sol will be a tuple, because you sort of returned it in this way, which sort of implicitly defines a tuple. But you can unpack all the values, so we have the names that we're more comfortable with. And then we can sort of plot. What we want to plot is the grid of our possible solutions and what the utility we got out of them was. And then we'll also plot what the Python found to be the best solution. And then you can sort of see, okay, utility is increasing in x1 and also in x2. And we found the solution somewhere around here. We can, if we turn on matplot widget, then we can sort of zoom a bit around. We can zoom in maybe. And this is, of course, it's a coarse grid, so we know that it should sort of be entirely smooth, and it's not. And that's because we don't have infinite many data points. But we can see that sort of, I don't know if you can see it, but it's found a point where utility is rather high. Looks like maybe a maximum point. Another thing, there's a question down here. You can invert the y-axis, or you can just like scroll around, and then you can see, okay, for some, wait, let's zoom around. I'll just go back, and then for some combinations of x1 and x2, so when both x1 and x2 are rather high, then utility is just 0, and this comes back to this loop with this condition that expenditure must not be above income, and if it is, then you just set utility to 0. So that's why we had this sort of flat area. Now there's a small task with sort of, it's quite there's an easy solution, and then there's a difficult solution, which is actually just the next section. But I mean, this is one way of solving this problem. We can see that sort of it's not perfect. You're not spending exactly 25% of your income on the first good, and we can also see that there's actually some of your income that is left on the table that the agent is not spending, which we sort of, they don't get utility from savings, so that doesn't make sense. So it's not a totally precise solution, so this could be done better. So the task is just to think about how it could be done better. And if you have like a coding idea, then I think you should try to do it and try to implement it, and then pause the video, and then we'll talk about it afterwards. Yeah, so hopefully you sat down and had some thoughts about how to do it. So the most obvious way to do it, easiest way, is sort of a brute force way to do it, is to simply just increase n1 and n2, so the number of grid points, and then you get a more precise solution just by default. We can see that now to all the digits we're showing, then income is equal to expenditure. But this sort of takes a bit more time. It's also like there are nicer ways of doing it. One of them is to sort of utilize that you don't have to calculate utility or loop through all of these possible combinations where you're spending more than your income. So we're using monotonicity as a fancy way of saying it. Yeah, and you're basically just using that you're always going to be spending all your income, and you'll never spend more than your income. So that's an important other part. So you sort of, we only need to check this line where you're spending all your income. We don't need to check all these combinations, because you're sort of, if you're saying I want to spend 10% of my income on good 1 and 20% of my income on good 2, then you're only spending 30% of your income, and we know intuitively that that's not a good idea for maximizing utility. And we did actually already defined, or the function has already been defined in our py file as another function, just a little bit lower down. So we go down to that. So the idea is just that instead of looping through both combinations of x1 and x2, then you loop through possible values of x1 just as a share of income spent on good 1. Share of income spent on good 1. And then x2 will sort of just be use what's ever left of your income. So income minus whatever you spend on good 1 divided by the price. That will be the number of x2 goods you are consuming. So now we only need a one-dimensional array for the possible x1 values. And we initialize possible x1, possible x2s, and possible utilities. Again, we sort of start from a guess of consuming nothing, and then we only need one loop through the x's, and then we loop through the x's, sort of increasingly spending more and more of our income on x1. And then we have the x2 implied by the budget constraint, so implied by this. And then we calculate the utility, and we no longer have to have the condition that we don't spend more than our income, because that's that condition is already used in this expression, so we know we're spending exactly what our income is. And then we can just calculate the utility instead of having this if-else condition. And then if that utility is better than the best one so far, then we'll use it. So that's what we get out of this, and we can see that the solution is already better. There's 1,000 grid points here, but it's actually a lot less total grid points than before, where we're using 500 times 400 different combinations of possible grid points. We can see maybe if we use 500, then you're still in a good area in terms of income spent, share of income spent, or total income spent. We can also see the utility here is 3.3885. Okay, it's actually smaller. No, 885. Yeah, okay, so it's slightly higher for our new solution, despite having much fewer grid points. I mean, it's not much, but it's slightly higher, using a more simple program and less computing time, which is always nicer, especially if you want to do this. If you want to expand on this, then it's good to have the most efficient solution. We can plot this solution. Now we can't really do a three-dimensional plot, because we only have the solution looping through one dimension. So what we do instead is to utilize the fact that you can have multiple subplots in Matplotlib. So we create a figure, and then we say we want to have this figure to have two different plots, which we do by initializing these arguments. So 1, 2, 1, what does that mean? It means that we want to have a subplot, and we want the subplots to have one row and two columns, and we want this to be the first of the subplots. And then we call it x left, and then we plot x1 values and utility values, and we also do a scatter plot with just the actual solution that we found, and we also have labels and titles, and then we also want a right plot where we plot the x2 values for the given x1 values, and we initialize this with the first two arguments are the same, one row, two columns, and now it's just the second plot that we're looking at, and then we plot in x1 values for different x2 values. And this is just a little extra thing that you don't actually have to show the figure when you define it. You can close it, and then you can just print it later. So this is the left plot, and this is the right plot, or axis. Yeah, and then we can see that we're maximizing utility for x1, and then we have the implied x2, so using this budget constraint to just say when x1 is this, then we're spending the rest of our income on x2, so x2 must be this. So this is how you do it manually, not manually, but manual programming. But the third option, which is typically the way to go, is to call a solver. So Scientific Python has a bunch of solvers, and that's the go-to way to solve equations in numerical Python. And it's a module that does a lot of things for you, and it does it in a very efficient way. Later in the course you'll learn a bit more about how these works, but the main thing for now is just to know what they are and how to make it work for you. There are a bunch of different options and different algorithms you can call and stuff like that. That's not really that important unless you're doing really heavy stuff. So now we just choose the parameters here initially. It's the same ones we've been working with. And I'll show you a few different functions. The first one is a scalar solver, so a function that takes one argument and outputs one. Sorry, a function that takes one argument and outputs one output. That's sort of the most simple solver. And we'll always be calling a minimizer, which is something in numerical computing that sort of, you never maximize something, you always minimize something. So all the SciPy stuff is always minimizers. So you just need to take the negative of whatever function you're trying to maximize. So value of choice is that we're still using this implicit condition that x2 sort of can be implied from x1, and then it's the negative of the utility for that given x1 and that given x2. So this value choice actually has multiple input arguments, but we'll sort of give Python or the solver the arguments for these arguments, or the values for these arguments, and then Python will always solve for x1. So we want a solution. We want a solution which we call solve case 1, and then we call this optimized module, and then we call the minimize scalar function from SciPy optimize. And minimize scalar want the function that we want to minimize, which is this function we defined up here. Then it wants a method. One method is bounded. There are like a lot of other methods which you can find in the documentation. You can go in and then you can look at the minimize scalar function. And then you can just see it here. It has Brent, bounded, and golden. Again, don't really worry about it. Bounded allows us to use bounds, which is nice in this case, because we actually have bounds, and our bounds are you can't spend less than 0, or you can consume less than 0 in good 1, and you can consume more than your income. And then we sort of give it the arguments, the rest of the positional arguments here. And that's just args, and then you give it a tuple of the remaining positional arguments. And that's actually how to call the solver. Then this function will itself figure out how to minimize this function, which is the maximize utility, under this bound. And then you can just unpack the solution. It's sort of, the solution is its own class, but it has like different attributes that you might be interested in. One of the attributes is x, which is the solution argument, so the x that minimizes this function. It actually also has solvecase.1.fun, which is the function value, but of course that's negative, and we actually want the positive version. So we instead just unpack x1, which is the solution to our problem, and then we imply x2, and then we calculate the utility, and then we print the solution, where we're using the function from our Py file. Yeah, I'll actually close down the Py file so you can see everything in the notebook, because we're not really using it right now. So that's, and then in this case, this would actually be the way to do it, because we're sort of, this condition always holds, so we actually just have a one-dimensional problem. But in some cases, you might have an actual multi-dimensional problem, where x1 and x2 are sort of not, or x2 is not implied by x2. In that case, you can use a multi-dimensional constraint solver. You can use multiple dimensional solver, and in this case, it will be constrained by the income condition. One method is SLSQP, which I actually don't know what it stands for. and you shouldn't worry about it. Not right now. There'll be a later lecture where you sort of learn of the different methods. Again, we want to define our objective function to minimize, and we want it to be the negative. Because this is a multi-dimensional function, it can sort of take multiple arguments, but the way SciPy wants those arguments to be ordered is actually just as one argument that is an array with multiple values, multiple elements. So it is a vector function, you can call it. It can take multiple arguments, but SciPy wants it to be one variable with multiple values. So you just have it as an x, and then we unpack it. So x1 is the first element, and x2 is the second element. And now, because we don't have that the income condition is implied inside our function, we sort of need to have it as a constraint. And how do you define constraints in an optimizer? Well, you do it like this, and this can sort of look kind of daunting, but what it is just a dictionary, and you can have multiple constraints. If you want it in a tuple, then you can have sort of like, you can write another one, but we won't do that here. And then you say, okay, the type of constraint I want is an inequality constraint, so that something has to be less than or equal to 0. You could also have an equality constraint and say, okay, this has to hold, not exactly, but numerically exactly. And then you have to define the function which sort of defines your constraint, which also takes the same x as up here. So the x1 and x2 in an array, and then our constraint is just the income budget constraint. So income minus expenditure, and then if expenditure goes above income, then this will be negative, and the constraint will not be met. So what you're basically saying by you want the type of inequality constraint is that you want this function to always be positive or 0 for the x that Python finds. Yeah, and we still want our solution to be bounded, though we just want the expenditure of x1 to be between 0 and all of the income, and the expenditure on x2 to be between 0 and all of the income. And we also have to give SQP an initial guess, which can sort of be anything. It just has to be within the bounds. It doesn't have to be a good guess. It's nice when it is, then it's sometimes faster. But it's sort of not doesn't necessarily have to be a good guess. At least not in a relatively easy maximization problem. And then it looks very similar to, so before we had optimize.minimize scalar, now it's just optimize.minimize for a vector function. And then we have the function, which is now this function that we're trying to minimize. We input the initial guess, and we put the arguments that you put into the function. And then we imply the method. Again, you can see on the website there are like a bunch of different methods for sort of minimizing function that can take multiple arguments. It's still a scalar function that sort of returns one output, but function that has multiple inputs. Yeah, again, bunch of different methods. You learn about some of them later. It's not really important here. What you need to know is that the SLSQP method can take bounds and constraint. The Nevermeet method can, but it's it's a bit more brute force. So it can sort of take more weird functions. Yeah, that's the most important thing. But don't worry if you didn't understand that entirely. It'll be important later, but then you'll actually learn it. So yeah, when we run this, so insert the bounds and the constraints, and then we get the answer out, and it's close. to what we know is the true value. It's just on the bit of the other side. So implicitly, because of numerical inaccuracy, then you will know there will sort of be some digits if you had more decimals here. So this is numerically very close to this. And when you're unpacking the solution from this function, then you can still have the sort of this x attribute, but now because you have that x is an array with 2 elements, then you can sort of unpack the elements separately. And the third case is to use a multiple dimensional solver, but not use constraints when you're calling the solver, like the way we do now, but sort of implement the constraints via penalties. This can sometimes be useful, but if you can do it like this, then I recommend you do it like this, with the constraints like explicitly defined. So what do I mean by implicit constraints via penalties? What I mean is just that you have this value function and you tell Python to minimize it, but if the x's violate our budget constraint, then you just give it a huge number, and it's trying to minimize this function. So it would think, okay, that's not a good combination of x's if I get a huge number from that. And this sort of, it introduces kinks into your value function, so it can become sort of harder to solve for the solver because it doesn't understand that it's constrained, or you don't tell it explicitly that it's constrained. So the way we do it is just that you have the value of choice. You can unpack x1 and x2. That's just because we're using them multiple times and then we don't want to refer to the array each time. You set your penalty to be 0, but if your expenses, which you calculate here, are higher than the income, then you create a penalty based on how much higher your income is to your expenditure. So that's here. So if your expenditure is much higher than your income, then your penalty becomes much larger. You also scale your utility to make sure that, or you scale your consumption of each good to make sure that the utility you're putting out is only the one implied by utility function. I don't think this is like strictly, I think it would work without it as long as your penalty is high enough, but this sort of ensures that even though there's a combination of x2 which does not satisfy the income constraint and thus gives you this huge penalty, but maybe it also gives you like crazy utility that actually outweighs the penalty, then Python will think that is the correct solution. So this sort of makes sure that the utility you put in here could also have been done by having x1s and x2s inside the budget constraint, and then you can get this utility without getting the penalty. So we still have initial guesses, but we don't have bounds or constraints now. We just have this function which we're minimizing, and then we use null meet because it's sort of, it does not take bounds and constraints, or at least it doesn't take constraints. I can't remember if it takes bounds. It does. But that's not important. And then we insert the arguments, and it works the exact way, and it finds the solution extremely fast. I mean, this is a simple problem, so all of this will sort of work relatively fast. So that works. Now I want to show you how to draw indifference curves, and this is sort of a new problem which can also be solved with optimization in very similar way. So to draw an indifference curves, then you need to solve the problem of finding all the combinations of x1 and x2 that gives you. So we're solving the indifferent curves for a given point of x1 and x2. We'll call them y1 and y2. And then we find all the x1s and x2 that gives the same utility as the initial x1 and x2s. So one way to do it is to fix a grid for x1 or x2, and then find the corresponding x1 which solves this condition of utility being equal to the original utility for each value of x2. Our objective function is now, instead of minimizing, we're trying to set it to 0 because we're trying to find an equalization point. So it just returns the utility function of whatever new x1 and x2 combination minus a u, which is the original utility, basically. So the way we do it is we have an I1 in our function here. We have an I1 and an I2, which are the initial points. We have an alpha and a number of grid points, and then sort of the maximum value of x2 that we want to see at the difference point at. So we calculate the original utility, and then we create an empty x1 vector, and our x2 vector is just this grid from a very low number to a very large number. Now we can't use exact 0 anymore, because we know from our utility function that if x2 is exactly 0, then the utility will be exactly 0, and then there's no x1 which can sort of set it to the original utility value. And then it goes from a low number to max with n grid points, and then you just loop through x2, and then you use this root function from SkyPy Optimize. And the root function just finds the root of the function. So this is why we wanted this objective function to be utility of x1 and x2 minus original utility, because we want that to be 0 at the indifference point, and that's finding the root. We have a guess. Initial guess is just 0. It's a bad guess, but it doesn't matter. And then we also have the arguments to the function here. And then we just do this loop and let SciPy solve our problems for us. So here we just define the function, and then we actually call it down here. We want to find the indifference curve for the 4.4 point, and the x goes from 0 to 10. We just call the function, and then we plot the solution, and then we see this was our original point, and this is sort of the indifference curves, and it looks how you would expect a conductor's utility indifference curve to look. Sort of as x1 is very low, then you need a lot of x2 to be just as happy as you were originally. Now there's a small task. Find the indifference curves through x1 equals to 15 and x2 equals to 3 and alpha equals to a half. So what we had here was that x1 was equal to 4, x2 was equal to 4, and alpha was equal to 0.25. Pause the video now and try to solve it. Remember that you're allowed to copy code from what you have already seen to solve this problem. Hopefully you solved the problem. Maybe you didn't. That's okay. The solution was basically just to copy all this code and then change the values for x1 and the value for x2 and the value for alpha here. And this is sort of a very easy solution once you know it. But it's not that far away from what you might end up doing when you're doing problem sets, because sometimes you've been shown something that is really similar to what you're doing, and then it's totally fair to just copy something and use it and change it as it needs to be changed. And the fact that you know what to copy and what to change sort of shows that you understand the code, which is the most important part. It's a bit of an ugly plot. No, it doesn't matter. Okay, so that was actually the main part of this lecture. You're very welcome to stick around if you want to learn more useful things, but it's a bit advanced. It's everything that we have been doing today, but inside a custom class, which is here we call it the consumer module. It's okay to take a break now, but sort of what you will get out of it is that you'll learn more about classes, which are really good, and you'll sort of see a whole example of how to make a class for when you're solving your own modules, and how to put those inside of classes and structure your code a bit more nicely. So yeah, I'll go through that at the surface level. So first I'll open the consumer module, so we can have it and look at it while we're looking at the notebook. How it works is you have this initialization function that sort of defines key parameters, baseline parameters, and then you can also insert a dictionary or keyword arguments if you want to update any of these. So if you just sort of don't say anything, then it will just get these parameters. So that's the initialization function. Then there's a string function, which just sort of prints different parameters for this consumer. And if the consumption problem has been solved, then it also prints the solution. The consumer has a utility function, which is again just Douglas, but you could actually change that without changing much of anything else, and still have it to the code work. Have the code working. Because the solution uses optimization and not like any tricks or anything, like mathematical tricks. So you just have the value functions, the negative of the utility function. That's our objective function, and then we're doing the exact same, calling an optimizer. Here we're using a multivariate optimizer, so we're allowing both x1 and x2 to vary, and we just have the income constraint explicitly defined, and then we say, you figured out Python. Before we're using also, like in another example, we're using the trick that you sort of know that you'll spend all your income, but here we don't bother with that. And then we store the solution inside the class itself. So we don't. This function does not return anything. It just sort of solves our problem and stores the solution. So here we create a consumer called Jeppe. You can see when we print him, then it calls this string function and prints out like key parameters. And then when we solve it again, or when we solve it and print it again, then we will also print out the solution. And this sort of the nice thing about this is both that you have things a bit more ordered. You have that all the parameters are sort of baseline defined inside your class, and you can sort of, these functions can call on each other. So you have the utility function here calling on itself, and the print function sort of automatically calls on the string function. And another thing is you can sort of define new consumers and give them different arguments or different parameters, and then you can use all the same functions very easily. So here we can create a new consumer called Mette, and give her a new alpha. And we can see that when we changes her alpha, that also changes her solution from our other consumer Jeppe. We also call the find indifference curves function, which does the exact same as we've seen, finding indifference curves. It just stores the solution inside inside the class, and also got to mention that it sort of finds multiple indifference curves. So it finds the indifference curve at the optimal level. So after solving the model, it finds the indifference curves sort of the solution, but it also finds the indifference curves for some one x2 combination that's not optimal, and one x2 one x1 combination that is outside of the budget constraint. You'll see why when we plot it, but it's sort of the base code is the same as we have already seen. And the reason we want that is we want to be able to plot these different indifference curves. And this is sort of everything's a bit nice. So we create the figure first and the X, and then the consumer module has like all of these really nice functions that can sort of add. First we add the indifference curves, then we add the budget set, which is sort of this red area, so possible combinations of x1s and x2s, and then we also add the solutions, just this red mark, and then we add details, which actually forgot what. Yeah, okay, that's just like labels and stuff. Yeah, and that's all inside of these small functions. I mean, you could even, I think, one thing you could do would then be to create a function called plot everything, so you don't have to do it like this, but then just say, okay, I want a function called plot everything, which is tied to the module itself, which just calls all these functions. Don't know why Python thinks that's an error, because I'm pretty sure that's not an error. And then you can just call meta.plot everything, then it should work. I haven't imported this. Yes. Alright. Again, that's because you have to, all the packages that you're using inside a Py file, you sort of have to import them inside the Py file as well. Yeah, so now PLC is defined. So we can call this function, then it works. And that's just sort of stacking all the functions inside the Py file. Yes, I think that was yeah, then there's a little note here about sort of what it means that you have a function, which is normally we call the methods, because they're tied to this class, the self argument, but sort of actually you can also use all of these functions without directly thinking of them as methods. So we have imported consumer, so you can call consumer.solve and then just input the class as an argument. Then it's the self argument here, while when you write Christian.solve, then you're just using it a method, and then Python implicitly has Christian as the self argument in the beginning. Yeah, it's a minor note. Yes, thank you for watching today. I hope you learned a lot.